My name is Ashley Kane, and this is my presentation of Lab 5, Magnetic Braking with Faraday for Physics 2212. The intention of this lab was to help us better understand the concepts of Lenz's law, Faraday's law, and flux through the observation of a powerful magnet being dropped through a conductive tube of an aluminum foil. Some important physics principles and concepts to understand for this lab are the magnetic field of a dipole or moving bar magnet, EMF of a moving dipole, Faraday's law, Lenz's law, and magnetic force. The two formulas that I use for magnetic field of a dipole or the bar magnet and EMF of the moving bar magnet are on the right. I also explain Faraday's law in the instance of this lab, and that the change in flux, which comes from the moving bar magnet as it moves closer to the tube through the area of the tube, will create an EMF across it, and because aluminum foil is a conducting material, that means that a current is also induced across the tube. Additionally, I included formulas for the current below. I also explained Lenz's law in the situation of this lab, that the magnetic field generated from the induced current in the tube is in the opposite direction of the change in flux from the bar magnet. Also, I included the two formulas for magnetic force on the loop and the gravitational force on the bar magnet. Here is the experimental setup for this lab, in which I measured the tube length to be 0.32 meters, the width of the material or the aluminum foil creating the tube to be 0.006 meters, the inner radius of the tube to be 0.02 meters, the outer radius of the tube to be 0.026 meters because of the width of the aluminum foil, and the mass of the magnet to be 0.024 kilograms. The procedure for this experiment is also included below, and what we did was mark the north pole of the magnet. We created the experimental setup according to the diagram on the left, as I recounted earlier. We recorded the entire dropping the magnet with a smartphone, and we used videos to determine the enter and exit times and calculated the total time that the magnet took to fall by doing this. We carried out these procedures 5 times, and I recorded the time for each trial and found the average time that the bar magnet took to fall through the tube to be 1.27 seconds. We then created a computational model for this experiment using the GlowScript IDE, and it created a velocity versus time graph of the falling magnet. I included the experimental measurements that I explained earlier, including the length, width, inner radius and outer radius of the tube, as well as the mass and the dipole moment of the magnet. The second segment of code shows a for loop creating the tube of aluminum foil and shows that this creation was created by segments of loops of conducting material. Additionally, I used the magnetic field formula that I showed earlier to create a function calculating the magnetic field created by the bar magnet at a certain location. Here I use the flux formula shown earlier to calculate the flux through one of the small segments of the tube. Finally, we had a while loop to show and display the falling of the magnet through the tube, as well as calculate the velocity at each point in which it passes through the tube and graph it on a velocity versus time graph. We did this by considering all the forces on the magnet, including the gravitational force and the force on the magnet from the ring. We also summed up the force from each ring to calculate the total force from the tube on the magnet in the upwards direction, and added them together to find the total magnitude of force on the magnet and on each ring comprising the tube. Using these values, we were able to calculate the velocity of the magnet to create the computational model and graph of velocity versus time. And here is that velocity versus time graph from the computational model, and it was able to calculate the time in the tube in seconds, and it calculated to be 1.319 seconds. In comparing the result, we found that the computational prediction, as stated before, was 1.319 seconds, whereas the actual time found was 1.270 seconds, and reasons for that difference in result could be additional unaccounted for magnetic fields or errors in measurement for the experimental setup. Finally, the first conclusion question asked if the resistivity of the conductor of the tube was reduced to 0, and what the falling magnet would look like then. And as stated in Ohm's law, the current in the tube would increase, and therefore the force upwards on the magnet would increase. Therefore, the magnet would fall more slowly and would completely stop falling. The resistivity was 0, and the force on the magnet from the tube was equal to the force due to gravity on the magnet. The second question asks what would happen if holes or slots were cut into the tube, and how would this affect the current in the model. And as I showed in the model, each segment of the tube exerts a force on the magnet, and they're all summed to equal the total force in the tube. So without some of these segments exerting a force, the total force will not be as strong, and the magnet will fall more quickly without as much resisting force.